Just give it a second. Awesome. Thank you guys for joining in today. In today's call, we'll be going over through initiative, a challenge that we took, collaborators took for past couple of months. And we'll go through the problem statements, the steps that we took to reach the goal that we started with to achieve. And finally, we'll look at the future work and as well as the team, and we'll conclude the meeting after that. So before I start with anything, I just want to welcome everyone from the UNICEF team, the collaborators of this challenge, as well as the Giga team here. So I'll just quickly hand over the meeting to Do from the Giga team and to introduce themselves and kick this call off.
Thank you, Kaushal. So welcome everyone. My name is Do-Young Kim, lead data scientist at Giga Initiative. Our mapping and tech team, led by Narwa, has been working on developing various ways of collecting accurate school location data to support the operations of Giga to connect every schools in the world to the internet. So as one of these efforts, we have been working with UNICEF Sudan country office and our partner OmdenaLore to develop AI-based algorithms to map schools using very high resolution satellite imagery in Sudan. Unfortunately, we may not have time to get your questions and answer them, but instead, please put your questions in the chat box. We will try our best to answer them. So now I will give the stage to the Omdena project team for the details. Thank you.
Awesome. Thank you so much, Do, for introduction and everything. So in today's call, we'll first discuss about the challenge, the problem statement, and the goals, and then we'll go through all the processes that we took to reach this goal. And then we'll talk about the future work as well as the team that took part in this whole challenge for past couple of months. So we commenced this challenge on November 6th last year. The goal was to basically connect the unconnected schools around the world, which is the goal of Giga team, ITU, as well as UNICEF as well. What we wanted to do was to utilize computer vision, deep learning methods to accurately and comprehensively identify school locations in Sudan from satellite imagery. Just to give you a context of it, so it's sometimes what happens is a country does not maintain or sometimes does not maintain a proper record of the schools that are there in the country. If they maintain it, sometimes it's inaccurate and as well as it's incomplete. So the one way to maintain those records would be a traditional way where you can go to each and every single location and map those out. But generally, these methods are very remote, inaccessible, and sometimes very insecure to go to that particular location. So what we wanted to do, and just as you can see on the right-hand side, what we did, what this particular example shows in Colombia as well. So we have the red dot shows the records that the country or government already has for the schools, and then using AI and satellite imagery, we map even more schools that were not accessible or were not in the record itself. So what we started to do, or what we aimed to do, was to build a deep learning model to do just exactly that. So on November 6th, collaborators from 31 different countries all across the world, as you can see from the far east, from Australia, and from the far west, Canada and US, we had 75 collaborators who were working on this challenge, and 30% of them were female collaborators. So now we have 6 different team members or team leaders that will be presenting their own challenge or own task that they worked on, or they led this whole task. Starting from the data team, the data inferencing team, Nashwa. So I'll just pass the stage to her to show what they did in their own task. So go ahead, Nashwa.
Okay. So our data set consists of 3 parts: a CSV file, a table with 20,432 rows and 179 columns containing data about schools in Sudan, like state, sorry, can we, okay. Like state, district, number of students, number of classrooms, number of teachers, but most important, the exact location, which is the longitude and latitude of the school. To train the AI model to detect schools in satellite images, we have two generated data sets. Schools that contains 6,560 images and non-schools containing 47,741 images. Next. To get the school images, we used high-resolution satellite image tiles around the longitude and latitude provided in the table. To get the non-school images, we got 4 images around each school from north, south, east, and west. So the one in the center is the school, while the other 4 are assumed to be non-schools. The resolution is 224 by 224 pixels with zoom level 18, which makes 0.6 meter spatial resolution for each image. The imagery were collected from Maxar's Imagery archive under NextView license. The imagery are collected from WorldView 3 sensor, were composited with R, G, and B bands using natural composite method. We used Tableau to create a set of interactive maps showing different measures that we extracted from the CSV file. So we have the distribution of available seats, average number of students per classroom, per teacher, percentage of schools with fences, schools in urban areas, and schools of boys and girls. When hovering in the actual dashboard, when hovering over a certain district, it shows the statistics. So, for example, here in Bara, the average number of students per classroom is about 33. While seeing the images in the school folder, we noticed some common patterns that repeated in school images, like this one bar, these 2 parallel bars, 3 bars, 4 bars, this U shape, this omega shape, this closed square shape, and one of the most common features is having trees in the playground. This bar chart shows the number of schools by state. The blue bars represent the total number of schools in the CSV file, while the yellow bars represent the number of images in the school folder by state. Although Khartoum, the capital, has the greatest number of schools in the CSV file, it has only 1 image in the schools folder. The next slide will explain this. We plotted the longitudes and latitudes in the CSV file on the map, and this was the result. Actually, we have a considerable number of points incorrectly located outside Sudan. We investigated these straight lines in the right, and we found that they were simply generated by adding constant values to longitudes and latitudes. The other bulk, which seemed to be in Libya and Tunisia, to the left, most probably they were generated by incorrectly entering the latitudes in longitudes column and vice versa. Another challenge we faced was having repeated images in the school folder. We found 564, which 8.6% of school images repeated. Some of them repeated more than 10 times with different names. We cleaned these data and saved them in another folder to be used in AI model training, validation, and testing. The non-school images were generated by taking images around schools, as we saw in a previous slide, but this didn't guarantee that they don't contain schools. Some images may contain schools like these ones, but as a non-school set contains a huge number of files, we couldn't get an accurate estimate of the percentage of school images in the non-school folder. That's all for data inference. Thank you.
Thank you so much, Nasha, for this amazing presentation. Now we'll move to the second task or the second step of this process, data labeling and preparation. I would like to invite Sanchit for presenting the whole slide. Yeah.
Thank you, Kaushal. Thank you, Nashwa. Hello, everybody. I'm Sanchit. I'll be presenting the task for data labeling and preparation. So the objective for this task was to basically identify the region of interest in the certain image, also dealing with data labeling and the reviewing process, and also to prepare unified data for modeling and evaluation. So next, please. So before I jump to the region of interest, let's just first understand what does a labeling means. So basically image annotation and labeling is one of the most important stage in the development of a computer vision application. So basically, for example, categorize the image into a tag or a label, basically in our case could be a school or a non-school. Now coming back to the region of interest, basically in knowing what area or what region to mark as a region of interest, we had a fairly good amount of discussion in the beginning of the challenge, basically to identify what should be considered as school or non-school. Also getting a lot of insights from the data inferencing task, having the common school patterns and the repeated patterns matching for the schools that give quite a fair amount of understanding. Also, what mentioned here in the slide is a document that was published by the Human Development Resource Center on the school building designs for primary and secondary schools in Sudan, in South Sudan, which is quite similar design pattern in Sudan as well. So basically that stated, so a school should be consist of 3 buildings, basically a main classroom building and the 2 adjacent building attached to a classroom building. All the 3 buildings should have an access to a veranda and also can consist of, for example, an additional space for kitchen or hand pump, etc. So we had quite fair amount of understanding what to be considered at school. Also keeping in mind that this was not certainly applied for all the images, so this pattern. So we also having a broader perspective of when labeling a school image, also considered like long elongated buildings which have access to open field like trees, having a small block connected to a part of the buildings also qualify as schools. So we also did labeling for those part of the images as well. So also keeping in mind with the design patterns that we have discussed. So moving on. So now basically the main task started with terms of labeling on the images. So we considered to label only on the school images, since basically that for the object detection for segmentation makes more sense to only consider school tiles. So for labeling, we worked on the image annotation tool called LabelBox, which is really impressive tool in terms of having working in the team and the collaborative labeling task, which was exactly for this project. Also, we had an access provided by Omdena since they had a license for this tool. And in the beginning, we had few sessions in order to understand or to get familiar with the tool itself. How do we proceed with the labeling? So as seen in the image on the left, this is a school labeled as a school tile. Also keep in mind, it's not just the building, it's the entire region of the school, including the boundaries itself. By looking at the center of the image, which image can consist of 2 school buildings as well. So we also keep in mind when we were labeling to also handle these cases to label and school when there are more than one in a certain image. And then far to the right, where we see it was really harder to classify or to label whether a tile consists school or not. So for those cases, we mark them as non-school. Yeah, so moving on. So as this task was sub-splitted into labeling and reviewing, so that also really helped us to review all the work we did on the labeling part. So in order to basically accept or reject and label which was done on those tiles, and also will help us not to have a misclassification or mislabeled on the images. Also, we make use of all the options, like, for example, the issues or the question section in the tool itself to clarify certain questions, like, is this a right approach to label? Is it really a school in that image or not? So a lot of clarification was also done in that aspect. Yeah, this is like an overview performance dashboard. So that's really impressive teamwork, the collaborative work that we had done on the labeling and reviewing. So the amount of hour that has been put in the task, considering also discussions from the beginning of identifying the region of interest up to the point to complete the label and reviewing took around 3 to 5 weeks, which is also really impressive within this time bound to complete within certain huge amount of data set that was provided to us. So yeah, that's an overview of the, and now moving to the data transformation and the preparation. So after we have done reviewing, we have exported that annotation or that label file from the tool itself, but later on realized that this was not in the standard format, the COCO format. So basically, COCO stands for the Common Object Context Dataset format. It's widely commonly used in the computer vision object detection domain, as seen here, that there are like bounding box arrays with X, Y, min, max values, segmentation, also referencing image name. So after all, with the reviewing and cleaning up with deleting the duplicated annotations, we ended up with a set of 5,223 annotation images that would qualify basically to move forward with the next steps to prepare a unified data set for modeling and evaluation. So having a standard data split between a train, a validation, and a test split with each labels, for example, for school and non-school, having that split of 80% to 10% and 10% each. So that would really helpful for the coming task to get started with. Yes, so I think that's from my side. Thank you. Over to you, Kaushal.
Thanks. Thank you so much, Sanchit, for this amazing description of what you have done. Next, I would like to invite Zoran to go over data preprocessing steps.
Thank you. Thank you, Kaushal. Hi, everybody. During data preprocessing, our main focus was implementation of the augmentation pipeline. Data preprocessing part of this project was important because it helped us generating some artificial data that wasn't present in the data set, and allows some variety in the training data set, which helps reducing overfitting. And because collecting enough of data is sometimes tedious and time-consuming process, it helps reduce time and costs of collecting the data. Next slide, please. So the main goals were implementing pipeline for generating augmented images. Next is the find solution for data augmentation, because there are a number of libraries out there for data augmentation. And finally, finding solution for storing those augmented images in some efficient way. Next slide, please. Before we started with augmentation pipeline, there were some challenges. like which augmentation library to choose and in what format to store images that augmentation pipeline outputs. So we further refined the goals into augmentation pipeline requirements, like pipeline needed to provide some functionality like reading information from COCO dataset JSON file, information about images and annotations. Also, it needed to apply some random data transformation to an image from a predefined set of allowed transformations. So in the augmentation pipeline, we used data transformations like blurring image, zooming in, zooming out, and horizontal and vertical flipping. After the augmented image is created, it needed to be stored in some format, and there are two formats that were used for storing the images. One is the plain original format for that's used for debugging and later inspection, and the final format that's used that is in TF records for files. Next slide, please. These are some of the augmented images that are created using this augmentation pipeline. On the left, you have an original image and the bounding box boundaries. On the right is the augmented image. On some images, only blurring transformation is applied. On some other images, beside blurring, also rotation transformation is applied. So it depends on image from one image to another what data transformation will be applied. Next slide, please. So at the end, the augmentation pipeline was successfully implemented, although not used much by the team. For the data transformation solution, the augmentation library is picked because it has intuitive and easy to work API. For storing images, the TF record solution was chosen because the main concern at the time was the amount of storage that would be needed for the augmented images. And the TF record solution provides a number of benefits, like it has more efficient storage use because the TF records data requires less space than the original data. Beside that, it allows partitioning data into multiple files for later faster loading. The major drawback with this solution is that visual inspection of the augmented images is not possible without first extracting information from TF records, and that would require knowing the data structure that's used for storing data. In our case, knowledge of some level of Python programming. And that would be it from me. Over to you, Kaushan.
Okay, thank you so much, Zoran. Moving on to super resolution. Harmala, would you like to continue here?
Okay, thank you. Okay, so for the super resolution, for that, we have used the generative phase prior, or the generative adversarial network, or the JFP GAN, to actually restore the satellite images from a low quality to a super resolution. Second is we wanted to enhance the colors of the school satellite images of the student schools. And of course, to also remove the noise from the raw satellite images into an optimized super resolution images. Next slide. Thank you. So for the before and after for school images, we have seen here there is an input images where it is much more blurred, and when we try to use the model or the GFP GAN, we have gained 5,223 school images, where we have at least 5,220 of them, which are processed completely in JFP GAN. And hence, we have gained 99.94% of the images that have been optimized with the use of the super resolution, which you're actually seeing on your right side. So, second, yeah, next slide. Okay, so this one is for the non-school images. So what we're seeing here that there are also 5,223 of the non-school images, which was actually randomly chosen from the total number of the non-school images. And as we process it in the JFP GAN, what we have gained is the 4,218 of it, which was actually processed on the JFP GAN. And hence, we have gained 99.90% of the images, which was optimized using into a super resolution images. So that's all for super resolution.
Awesome. Thank you, Amalan. So just to recap, we have already gathered the data or given the data. We have done inferencing on it. We have labeled the data set. And we have tried to augment the images to make even more refined data set or even more number of data set. And then use super resolution to increase the resolution of images so that like our AI model performs better. Now coming to the AI part or the creating the AI models, we'll come to the modeling task. And I would like to invite Roman to continue from here.
Hi everyone, I'm Roman and I'm here to present what we did as part of the modeling team. So as a part of the modeling team, we have come up to develop a model to classify schools with fewer false positives and false negatives. Sounds too technical. I'll explain what a model is and what false positives and false negatives are. The next slide. So modeling is essentially creating an algorithm which teaches a program to learn a specific task. It's kind of like emulating a real world problem into a computer-based program. So in case of deep learning, what happens is you give the model tons of data and tell it to extract features and patterns from it. And at the end, you tell it to perform a particular task. For example, it could be object classification, object detection, or segmentation. So that is what a model is. And about what I said, fewer false positives and false negatives. So to evaluate a classification model, we have something known as a confusion matrix. And it is essentially laying down an array talking about the real labels, which we have from the data, and the predicted labels, which we have from the model. We laid down for the true positives, false positives, false negatives, and true negatives. And as we see the formulas out here, we have the precision and recall. So we were working to get a really good precision and recall. That is a comparison of how much false positives we have in comparison to true positives and how much false negatives we have in comparison to true positives. Next slide. So we have had several different approaches. One of the most innovative one is out here, wherein we have a two-stage model. The first one classifies if it's a school or not non-school, and further it is later used to localize images using the sliding window technique in order to get an object detection kind of output. So we take a 256 cross 256 satellite image, pass it into a VGG classifier, and the classifier tells us of how confident it is, if it's a school or not. If it crosses the confidence threshold, we pass it on into an image splitter, or else the program ends over there. So what the image splitter does is it takes a 256 cross 256 image and it splits it into several smaller blocks. And those smaller blocks are passed on to a CNN classifier, which says if that block contains a school or not, and with how much confidence it is sure of that. The only difference between the two models is that in the first case, we have two classes, that is school and non-school. Whereas in case of the CNN classifier, we just have one class, that is school or nothing at all. Then once we have processed all the smaller windows through the CNN classifier, we take the top n confidence scores and then combine all these windows in order to have a localization of the school in the image. For the first classifier, we trained it for high precision and recall as the problem requires. And for classifier 2, because we had just one class, we just needed to make sure that it identifies school rightly in the given image. So the second classifier was trained for high accuracy. So next slide, yeah. VGG16 sounds pretty random. VGG stands for the group which actually came up with the algorithm, Visual Geometry Group. So essentially what happens in most of the deep learning models is that you take an image, you extract the features and patterns from it, compress the density of the data contained in the image to smaller and smaller blocks as it passes further down the blocks. So you have convolution and pooling layers, multiple blocks of it to extract features and patterns. And then finally at the end, you send it to multiple layers, which learns particular patterns. And then at the end, you have a softmax layers depending on the number of classes you have. Next slide. So the results of the first model is out here. We got an 89% precision and 84% recall. And for the second classifier, because it was trained primarily for accuracy, we have a 95% accuracy on that. So overall precision and recall of the combined model is the same as the first classifier. Next, we had one more innovative approach to the solution, that is a custom unit segmentation model, wherein you had two branches of unit. One is to process the mask of the image, as you see in the center plot, and the second one is to process the borders of the image, as you see in the right plot. What happens with this is that the redundancy of the data, it increases, which improves, or which should rather improve the chance of having a better precision. Next slide. This is how data flows in the custom unit. So we have two unit branches, one for the borders and mask, as previously mentioned. At a particular point, you transfer the data over to transfer the data over from both the branches, and then concatenate them and further have a few more convolutional layers before having the final output. Next slide. So it looks something like this. The first column, you have true masks. In the second one, you have the predicted mask. And in the third one, you have an overlay of the true and predicted masks. Here are the results for the unit segmentation. A lot more could be done in this case, but we have a 48% precision, a 10% recall, and a mean average precision of 0.2. Next, we had the YOLO V5 model. You only look once, and not you only live once. We took two models out of it. One is the YOLO V5M, that is the medium model, and YOLO V5L, that is the large model. So we trained the medium model on the super resolution as well as the normal data set to actually compare if super resolution gave better results as we expected or not. And in case of the YOLO V5, a large model, we trained it on the normal data set with two models which were different in this case. So in the first model, we just had one object detection output, and in the second model, we had two object detection outputs. This is what I mean by one detection and two detections. Next slide. So as we see over here, comparing the first two rows, we have the super resolution data set versus the normal data set. And if you look at it, the precision and recall of the super resolution data set is higher than the normal data set by somewhere close to 1 to 3%. Like precision is higher by roughly 3%, 2 to 3%, and precision by 1%. Similarly, if you compare the medium and large model, the large model seems to have a slightly better performance in recall. And coming to the number of detections, we see that having two detections increases the recall of your model. Next slide. And finally, we have the efficient Det model. Efficient Det is a state-of-the-art object detection model, which was based on having efficient net as the backbone of the model. It has a pretty light architecture and therefore faster inference. This model we trained on both the super resolution and normal data sets again. And currently, this is the model which has the best precision and recall values. As we see over here, for super resolution, we have 90% precision and 92% recall. Finally, a lot more can be done. Right now, to evaluate the confusion matrix, we use the intersection over union as the primary threshold. So what happens with that is when your IOU is low, your model, the confusion matrix generated actually predicts a non-school rather than school, even if your object detection model did predict a school, as we see over here. The model predicted a school over the entire fence of it, but the label actually had a very had just a building of the school segmented out. So the IOU was pretty low. In such a case, you would actually have a false negative. This could be due to the non-uniformity in the way that the data was labeled or presented to the model, which is why the model actually learned to identify the fence of the entire school rather than just the school building. So a lot more can be done in this regard by looking at the false positives and false negatives, and further probably cleaning up the data to help the model learn better. So this is what was done by my team at modeling. Thank you so much.
Thank you so much, Roman, for explaining what the modeling team did. Generally, what happens in an AI project is that the project ends here. When you create a model, you have predictions and you can run the predictions. The model ends, the whole project ends here. But in Omdena, we believe that it's not just about creating the model, but it's also about deploying the model so that like real people can use it in the real world. And that's why we wanted to have another step, which is testing, to actually test out that the code that we are creating is actually deployable. It's actually usable by UNICEF, ITU, and Giga. So we had a testing task as well. And to explain what we did in testing, we have Abid here. So I would like to invite him to present the testing task.
So, hi guys, this is Abid. I think we talk a lot about testing and software testing, and we don't really talk about ML testing, machine learning. Testing is a little bit tricky, and no one is really using it in, like, most of the companies don't even use it. They test a model, they think it works, they track their model, but they are not testing the code, they are not testing or debugging or logging most of the things that they should do in order to reproduce, or if there's something wrong, or if there's something went back, they need to go back and check. So we were also new to this machine learning testing, which is adopting a lot of techniques from software engineering side, software testing, and then how we started looking for the blogs, articles we share with knowledge, and our group, we had weekly meetings. We talked about how to deal with the topic, and looking at various ML testing projects that we can use and implement into this, similar projects, and that have inference, that are augmentation pipeline, because we need to test all of this so that when you have to create a commit, like push a code or something like that, it should be pre-push or pre-commit, so the testing will automatically run. It shouldn't be like like when you push the code into the production and there's error and your whole system breaks down. So that was our vision. So we started with next. We created a life cycle because this was new. We need to create some system steps to follow so that these steps can be followed and we can reach the final goal. So whenever someone complete the task, let's suppose data augmentation team have completed certain tasks and they have pushed the code, and they have labeled it as testing in a green testing. That means it is ready for testing. No changes will be required. So it will be assigned, then those tasks will be assigned into the groups, and the testing team will start working on that. And first we'll create a testing unit, simple testing unit using PyTest or very simple test like assert equals to, and then we create like whole function. And after doing local testing, because after creating testing, we need to test test it locally. Then when we are finished, we are going to create a pull request. So it could be integrated into the Omdena ecosystem. So whenever someone wants to test their code, like they have made like added some function or made some change, they can run that test before pushing the code. Say that no, the code is running and it's bug free. Next. Till now, there's no like code that is necessary to be tested for data inference. There's no code for like data collection. There is some script for data collection, but it's not. It's very simple. So we focused on data processing. We have completed and tested both data pre-processing, and they have been like created pull request. We have created super resolution and modeling. So these all are completed, and these three are more core, like they were more needed and more core components of these projects. So the insight, yes, testing ML is hard. Like we had a lot of workflow challenges, communication challenges, and people really don't know like how to create like use like deep learning libraries. And even I didn't know how to use deep learning libraries to come up with the solution or create a testing unit. It's hard. So that was our insight that it's hard. We need to figure out some simpler things. So we have created like we have shared a lot of ideas. We have created a lot of guides so people can also learn from it. And next thing, we resolve the workflow challenges. Like before that, we literally didn't know who is doing what. Now we know if there's a tag, we need to start working. If someone have created a pull request, we need to start working, and we need to start going. It's a circular motion, like in a project, in a typical project. So we also learn various ways to use other libraries like Hypothesis or, but we mainly focus on PyTest, and we focus on creating more effective and industrial standards, because it was used for mostly industrial standard. But we were also looking for like more deep learning and machine learning type of ML testings. We also focus. We have also used like a lot of inbuilt like TensorFlow, and also use other assert to check various things. So so the future work of so we will be working for the future work. We will be working on automation. So instead of like doing this manually, currently we are doing it manually because we have to test it on our own system. Then we have to push the code. For the future, we are thinking about making automation. Like when you push the code, the server will create like there will be a webhook or something. It will run, check the code is correct. It will then tell like tick tick tick, like in a GitHub. It will check tick tick tick. If all are the ticks, then it will tell the maintainer that it's good to go, and you can just like commit it into the main branch. So this will solve a lot of problem in debugging and resolving issues. Even if you have a bad code, you will know immediately that where is the bug. Because yeah, that's it.
Awesome. Thank you so much, Abid, for explaining what the testing team did. Believe it or not, this was one of the most innovative tasks at hand in this project, because ML testing is not very rich in this current scenario, because nobody, or very few people do testing on ML code and stuff like that. So it was really very interesting to have this task in hand. So we still have a good 13 minutes with us. So if you have any questions, please note, comment it down on the chat and we'll try to answer that. So talking about the future work, this whole project was based on OmdenaLore, and OmdenaLore is actually an open source project where collaborators come from all over the world to commit code, which can help other organizations, NGOs, startups to accelerate their project in their own company. So if you're interested and if you are someone who would like to help these organizations to do good in this world, you can come to OmdenaLore as a collaborator and help continue rebuilding either this project or any other project in the future as well. So for this particular project, our collaborators as well as other collaborators outside the OmdenaLore community would come and help us refine these models using OmdenaLore. And by refining, I mean, hyperparameter tuning and stuff which Ramin mentioned in the modeling slides as well. We also want to run the whole model into other satellite images. It could be Sudan, so neighboring countries, to detect even more schools and maintain a record out of it. And we also would like to retrain the model on more schools and locations and countries. So this was just for Sudan. So we would like to have more data so that we can even cover more countries. As you know that schools, the location, the structure of the school buildings might vary from countries to country. We would require to retrain the model for different country or a completely separate region, if you see like that. Also, as Abid just mentioned, that we want to do automation and testing, and even right now we can even have more test cases and pre-commit testing for reliable deployment, so that in future we can deploy everything that we built in this past couple of weeks to actual environment and maintain a record of all the schools. And that's all. And I really want to thank all the presenters and the task leaders. I know Kamal was not able to present something, but he had a huge hand in managing task 3 as well. So thank you to him as well, and all the task leaders and presenters to present what they did. And also thanks a lot to all the top contributors of this challenge. You guys really did an amazing work, and building an AI model in 8 or 9 weeks is not an easy task, and these guys did that voluntarily, and that was something amazing. So thank you so much, and thanks to Giga team as well. We have Rasha from Sudan office, and she would like to say something. So I would like to invite her as well to please go ahead and take the stage. Rasha.
Hello?
Hi, yeah, we can hear you, yeah.
So I just wanted to thank the team who has worked on this project. Just to give you an insight, this data won't be only very useful for Giga, but for the country as well to build on education. There's a lot that can be done having data and working on it to be able to reach children. We are trying to reach children generally for access to provide access to quality education in Sudan. So we are working to be able to provide internet and also advocate for using e-learning in schools as much as we can and to leverage technology. So I would say thank you to the team that worked on this to make it to make us walk a step towards what we want to achieve. And thank you very much.
Awesome. Thank you for sharing that, Rasha. Another huge thank goes to the Giga team as well, who brought this project to us and helped us through the whole project, like having questions about any satellite images or any questions about the data. They really helped us out. So I would like to invite Do and Ike to give their closing statements as well, if they are to.
Okay, thank you so much again, and we really enjoyed working through all these progresses. And we as someone mentioned in the presentation, we are looking forward to scale this, the results of this algorithm development into the entire country of Sudan and even for the other regions and countries. So we're looking forward to continue this collaboration. Thank you.
Awesome. That's such a great news to hear. Thank you so much. And somebody asked that if this code is open source or not. Yes, this whole code and everything is actually open source. So if you want to look at the code, all you have to do is to go to omdena.com/OmdenaLore and apply to become a member of OmdenaLore. You'll have the access to the repository, and you can even contribute anything you would like to contribute and become part of the community as well. And that's pretty much it, guys. Thank you so much for joining in. Thanks to all the collaborators one more time. And really great to hear you from guys. Have a good day until next time.
Bye. Take care.
Bye-bye, guys.
Thank you. Bye-bye.
Bye-bye.